In this video, we're going to discuss the density of a gas. One of the defining points of gases was that unlike liquids or solids, they don't have a set volume, which means for the same amount of stuff, you can change the size of it and therefore change the mass over the volume, the density. How dense your gas is depends on the mix of temperature and pressure to adjust the volume of that sample of gas. Let's take a look for a second and think about the ideal gas law. PV equals nRT. Well, moles. So, how do you know how many moles of something you have? Well, if you had a mass of it, like say 10 grams of a gas, you would need to know how many grams of that gas in 1 mole of that gas. And you could convert it into moles. You would need a molecular mass. What this really means is that if you ever have your mass divided by your molecular mass, so 2 capital M's here, that is going to give you your moles. So we can go back to our ideal gas law. We can actually trade out N for mass over molecular mass. If you knew the weight of your gas and you knew the molecular mass of it, well, you could find the moles and plug them in. And so mass divided by molecular mass will give us the moles. But this lets us rearrange our equation a little bit. Because what is density? It's mass over volume. And I have now mass and I have volume. If we rearrange, we multiply molecular mass up, we divide RT down, and we divide volume over. What we will find is that we can recreate an equation that says that the pressure times the molecular mass divided by RT is going to be equal to the density. You can always find the density of your gas if you know the molecular mass, the pressure, and the temperature. Let's do an example. Let's say I have a beaker and we fill it with nothing but N2. It's 1 liter in size. The pressure today is 1 atmosphere. It's freezing, 273.15 Kelvin. If I wanted, I could solve the moles. I could say, hey, how many moles is that? And I could find the weight of it, and then I could plug it into the 1 liter. We could set up PV over RT is equal to N. 1 times 1 liter, 1 atmosphere, 0.08206, 273.15, 0.0446 moles of gas. Because we know it's dinitrogen, 0.0446 mole. 1 mole of N2 is 28.01 grams. There would be 1.249 grams of N2 in the 1 liter container. So we could find the density of N2. We'd say, hey, it's 1.25 grams in 1 liter. Very small weight. Gas is very spread out. Density of gas tends to be pretty small. Remember, water is a gram per milliliter, so this is, well, not quite 1,000th, but it's well down there. Well less dense than water. But instead of going through all that trouble, I can just solve the density for my N2 by plugging in our values over here. I know the pressure, it's 1 atmosphere. I know the molecular mass of N2, it's 28.01 grams per mole. R doesn't change, 0.8206. Atmospheres, liters, mole Kelvin, and temperature, 273.15 Kelvin still. Run that 28.01 divided by 0.08206 divided by 273.15. And surprise, surprise, 1.249 grams per liter. Think about our units for a second. Atmosphere and atmosphere cancel, mole and mole cancel, Kelvin and Kelvin cancel. My grams and my liters are left in place. Different tools for different ideas of what you want to calculate, but the density of a gas can actually be calculated just by knowing the molecular mass. Conversely, though, if you know the density of the gas, you can solve the molecular mass, which is far more often the case for what we want to do. Often in a reaction, you will have a flask, materials at the bottom, and they'll give off gas. You can pump that gas into another container. You basically have liquid, and you invert a cylinder into it. The bubbles from the gas will go up. There was originally water in the container, but as the gas shows up, that water level goes down. As the gas fills more and more, the water level will go down as the gas takes up the top. You can capture that gas. This is a fairly common component of chemistry with gases, is when you emit a gas from a reaction, you can capture it. Well, by knowing the volume of that gas, and knowing the weights of the system beforehand, you can actually determine the weight of that gas, which means you can determine the density of that gas and solve what molecular mass it must have been. Well, very few gases have the same molecular mass. There's really only so many super common gases that show up in modern chemistry. Earth only has so many gases that are on it and stable for terribly long. And so generally you're going to show up with one of a small selection. As a result, if you know the molecular mass, you can tell what the reaction did. Did you make carbon dioxide? Did you emit oxygen? Was ammonia produced? By being able to use the density, we can solve the molecular masses. So this density relation is a handy tool for identifying the species of gas that you're working with.